just as a few reminders, the final is, if you're in the online section, which you guys are, is available now. It's been available for 3 months. And it's in the testing center. It's the same format as the other exams. It's on Canvas. It's multiple choice. It's the same stuff. The difference is this. It's longer. It's got 97 questions as opposed to the 66 on exam 1 and the 80 on exam 2. And it covers every chapter. And it covers them relatively equally. There are several questions about levels of measurement, stuff from chapter 1, and things about the shapes of distributions from chapter 2. It's all on there. Yeah?
It's going to be almost the same questions of the chapter 1, chapter 2, you copy and paste? Or
No, nothing gets copied and pasted. They're similar. In fact, here's one really important difference. I did not write this exam. I wrote everything else, but I wrote everything else by looking at the final exam and categorizing all the questions by chapter and I would write my questions by, basically for each question on the final, writing 5 related questions and then throwing them across the quizzes and the post-tests and the exams. So I've made it as similar as I can. It's not going to be identical. None of the questions are exactly the same, and the phrasing is, I've done my best, but it's a different person talking. So on the other hand, the practice final was written by the same person who wrote the real final. So if you want to get an idea for the difference in phrasing, do the practice final. And again, I give extra credit for that. And as something to remember is that for the practice final, if you want full credit for the extra credit, you have to get 100%. But that's easy because you can take it as many times as you want, and it'll tell you what you got wrong. And I have 2 hours of videos that explain every question on the practice final. So avail yourself of those, especially so the real final is not a shock in whatever difference in voice there may be. Like the other exams, you can't take any notes. You can't use the web. You can't have any formulas. It's all memory. Take a calculator, but that's the same as the other exams. 2 other things about the final. I have said in the past that I adjust exam scores. If the highest non-outline score is not perfect, then I add enough points onto everybody's score to move the whole distribution up high enough so that person now has a perfect score. That almost never happens on exams 1 and 2 because I usually get perfect scores. It never, let me rephrase that, nobody gets a perfect score in the final. It just doesn't happen. The final's hard, and you need to be aware of that so you can prepare and take it seriously. In the past, I've added anywhere between 5 and 15 points to the scores on the final. So you need to be aware that when you take the final in testing center, the grade that they tell you is not the grade that you're going to get. Your actual grade will be higher, but I can't say how much higher until everybody's taken it, because I have to see the entire distribution before I can adjust it. The other thing is once I adjust the score, so this happens after I make the adjustment, I then look at the percentage you got on the final, and if that's better than what you got on exams 1 or 2, I replace those earlier grades with the grade you got on the final. So if you've done poorly on one of the exams, this is an opportunity to make up for it. It can make a huge difference. The only qualification on that is you have to have actually taken the earlier exams. I don't replace zeros. And as I mentioned a moment ago, I think it was before we started recording, you have to get at least 50% on this exam before the adjustment to pass the course. There's 97 questions, so that means you have to get at least 49 of them right in the testing center, or I'm not allowed to pass you. Okay? That's a departmental requirement. That being said, I expect you to do better than that. So, hopefully that gets your attention and you're ready to do this stuff. So we're going to review the things for the exam. I'd like to start by answering any questions you have about the material in the last 4 chapters, 9, 10, 11, 12, t-test, analysis, variance, correlation, regression, and chi-squared. If we finish those, we can go back to material from the earlier chapters. Although, really, in answering these last 4 chapters, we will cover stuff from 6, 7, and 8, and some of the others as well. It just works into it. So, tell me what you would like me to talk about from Chapter 9. Chapter 9 is t-tests. Yes?
I think it's kind of covered, I don't know if it's like every single question, but most of them, when I took the quizzes, most of the things I had it wrong.
She's nowhere close to the microphone, so I'll rephrase the question. It should be. Yeah. I will rephrase the question so you can hear it. Because we got microphones here, but you have to push the button, don't you?
Okay. So on the quizzes, when I got them wrong, I would review it and then, figure out why, and it made sense to me. But the one thing that I just really never was making sense to me is figuring out the null hypothesis throughout those chapters.
Okay. I can give you an example of how the null hypothesis works for a t-test. That's Chapter 9 material. Why don't we run through the whole process, okay, from start to finish, so that there's 3 kinds of t-tests. Three kinds of t-tests. The kinds that we have are, number 1, we have a one-sample t, and that's for when you're comparing a single sample mean, to a known population mean. That's also the situation in which you would do the one-sample z-test, which was in Chapter 8. The difference is the z-test, you have to know the population mean and the standard deviation. The t-test is for when you have this hypothesized mean, but you don't have the standard deviation, and so you have to use the sample standard deviation as a stand-in. That's when you would use the t-test. So we have a one-sample t for when you're comparing a single sample mean to a population mean. We also have a repeated measures t-test. And that's for when you're comparing scores at 2 points in time, for instance, before and after an intervention, or at the beginning and at the end of a course. And you want to look at changes. Now that one's really easy because all you need to do is you take the person's score at time 2, you subtract their score at time 1, and that gives you a difference. It tells you how much each person's score changed. And the reason you start with time 2 is that way, if it went up, then you get a positive number, which is easier to deal with. So that's a repeated measures t-test, or a repeated t. And again, you just do the subtraction, and then it's exactly the same as the one sample t. The third version that we're going to talk about in this chapter, we may not talk about it tonight, is the two sample t. And that is when you are comparing the means of 2 separate samples, which is something that we haven't done before. We've only talked about one sample at a time. So this is if you have, say, for instance, you have an average score on something for women, and an average score on the same thing for men, or for people in 2 different college majors, or people who are married or single, or something like that. You're comparing 2 groups. And you would do this one to compare their 2 means. Now, let me take the example of the one sample t because it's conceptually the easiest. And the other ones are just variations on it. So the one sample t, what you're going to do is you're going to compare a single sample mean to a population mean. So let's write down a little bit of information. So let's say we got a sample of 16 scores. And let's say that that sample has a mean of 56. I'm just making, the variable, whatever. And the standard deviation for that sample is 4. Okay? I'm just making these numbers up. And let's say we're going to compare them to a population with a mean of 50. Okay? So what we do is we want to see if this sample mean of 56 is statistically significantly different from this population mean of 50. Now, obviously, the 56 is bigger than the 50. But the idea also is that if you were to draw another sample of 16 scores, it probably wouldn't be exactly 56. It would be a little lower or higher, and things move around a little bit. So you need to do the inferential test control for the variability that's in there. So here's what we need to do. We're going to do a hypothesis test. You can frame this in a few different ways. Let's start by actually writing what the hypotheses are, okay? In a hypothesis test, you have two hypotheses. You have HO, which is the null hypothesis. Null means empty or nothing's going on hypothesis. And you can word that in a few different ways. The way that I'm going to word it, this is the language that I use, but to me it makes sense. Hypotheses are always written in terms of population parameters. So, this is a population parameter over here. That's easy to deal with. What we need, though, is the population mean for the population that this sample of 16 scores came from. So we're not comparing the sample mean to the population in the hypothesis. We're comparing this population mean to this population mean, where this sample mean is an inexact representation of the population mean. So what I do is I write two different mu's, because mu is the population mean. And I put a little subscript. I put S for sample, so that's the population that the sample came from. And then over here I do mu sub C for comparison or control. Those are subscripts that I use. I don't know if other people use them, but they make sense to me. And the null hypothesis is that there's no difference, usually, if we're doing what's called a two-tailed or non-directional test. So I'll just say the null hypothesis is that those two are equal. I'm assuming that any actual observed difference in that case is just random chance variation. And if I were to repeat it, I would not get that kind of difference. The alternate hypothesis, or alternative hypothesis, you can write it as HA for alternative or 1, 0, 1, or is the mutually exclusive complement of this. And that's really easy. When you're doing a non-directional, equals is your null. So for the alternative, you just go that they're not equal. And again, remember, we're talking about the population mean, not the sample mean, but the population that it came from. So these are our hypotheses. So here's a little bit of data that I made up. Here's our hypotheses, and now we get to do the actual hypothesis test. The way we do that is by computing a value for t. All right? Now the formula for t looks like this. I'm going to scoot over a little bit here. It's actually pretty simple. I'm going to use a capital M for the sample mean just because I wrote it that way over here. We're going to get the difference between the sample mean and the population mean. And if you want to, you can put this here to make it clear that we're talking about our comparison population. So we get the difference between those two means, and we divide it by the amount of variability that we would expect at random, and that is the standard error. Now, because this is the t-test, I do not have the population standard deviation. See, I only have the population mean. And so I can't use the sigma sub x bar that we used for the z-test because I don't have the population standard deviation. Instead, I'm going to use the sample standard deviation. And when we do that, the name of this is slightly different. It's actually referred to as the estimated standard error. But you can also just call it the sample standard error, and you know what you're talking about. Now, that one has to be calculated separately. I'm going to come over here. It's a really easy formula. All we do is we get the standard deviation of the sample, and we divide by the square root of the sample size, right? So our standard deviation is 16. That's what I got right here. I'm sorry, that was the sample size, my mistake. There we go. There's the standard deviation, 4. Good thing I didn't get too far. The sample size, n, is 16. So we take our standard deviation of 4. We get the square root of 16, which is also 4. 4 divided by 4 is 1. So that's our standard error, or properly our estimated standard error. So what we do now is we come over here to this side, and we just fill this information in. So now we need our sample mean, which from up here is 56. So I'm going to come back down here and do 56 minus the population mean, or the mean of the comparison population, and that one I have right here, I made up as 50. And divide by the estimated standard error, which is 1. 56 minus 50 is 6 over 1. 6 over 1 is equal to 6. Okay, so what I have is a t-score for this sample. Here's my sample. They are 6 estimated standard errors above the mean. Right? They're only 6 points, and the standard deviation is 4. So if you gave them just a z-score, they'd be 1.5 standard deviations above the mean. But when you're doing an inferential test, you need to take into consideration the sample size, and that's why we use the standard error, the estimated standard error. So they are 6 standard errors above the population mean. Now, to decide if that's a big number or not, we need to compare it to a critical value. And the way that works is you have a distribution. It's a t-distribution. There's 0 in the middle. And we need a value that puts 95% of the distribution in the middle. That marks off a little bit at the top and the bottom, so that's 2.5% right there, and that's another 2.5% right there. That's 5% altogether. That's also the alpha. Alpha is the probability of a type 1 or false positive error. Now the trick is, when we did this with a z-test, we just know that we use the normal distribution, and those numbers are always plus 1.96 and minus 1.96, not with a t-test. A t-test uses a different distribution, and you have to know the degrees of freedom. Because the smaller your sample, it's like you're taking this and you're sort of squishing it down, and it spreads out. And so the critical values that you use are going to be bigger than plus or minus 1.96. Now, the degrees of freedom for this particular test is equal to n minus 1. So it's going to be 16 minus 1 is going to be 15 degrees of freedom. I just go to the web, and I find an online calculator, and I get the critical value for 15 degrees of freedom. It's easy to find. But I'm not going to do it right now. Let's just imagine for a moment that the cutoff is like 2.14. I'm making that up, okay? Because I would need to look it up. But let's say the critical value that separates the middle 95% of the t-distribution when there are 15 degrees of freedom from the most extreme 5%, which puts 2.5 up here and 2.5 down here. Let's say that's a value of t of plus or minus 2.14. It's going to be somewhere around there. Well, you know what? That's not a problem, because the value that we got for our sample is 6. So that's 1, 2, 3, 4, 5, 6. It's going to be like out here. So it's enormously different using the criterion that we did. And so what we would say is that this sample, the mean, is significantly different from the hypothesized value of 50. So that's the hypothesis test all the way through. And we would reject the null hypothesis. We just kind of cross that one out, and we would, by default, if we reject this one, then we must, be using this one. Now, please note, I don't say that we accept the alternative hypothesis, because this test only addresses the null. That's why it's called null hypothesis testing. It only addresses the null, but we have it set up so if this isn't the one that we're going to use, then it has to be this one. And so we conclude that the population mean for the population that this sample came from is significantly different from this population mean. So that's the significance test every step all the way through. That makes sense that time around? Okay. And let's just say for a moment that if instead of having a value of t of 6, let's say that we got a value of 2. All right? What that would do, get at my other marker, is I would put the sample value right there. That's in between our cutoffs. It's in the middle 95%. And so if our sample statistic, our value of t, were 2 instead of 6, we would not reject the null hypothesis because we say, well, it's different, but it's not very different, where we have a very clear criterion for what constitutes very different. And that means we looked at this critical value and we're using an alpha of 0.5, which is what you use unless you have some good reason to use something else.
So when it's in 5, that is 5%, we said that we don't reject the null hypothesis.
That's right.
But if it goes over there,
That's right.
so we say that we reject it.
Right. So on the outside, in this little area that I shaded off, that's when you reject the null hypothesis. If it's anywhere in between, you do not reject the null. Sometimes they say fail to reject the null hypothesis or retain the null hypothesis. Those two things, retain the null hypothesis and fail to reject the whole null hypothesis, those mean the same thing. In either case, you do not have evidence of difference using the criterion that you set up. Okay, so that's a t-test all the way through. Other questions about t-tests? Chapter 9.
It's going to be problems like that on the test, right?
No.
Oh.
Because this is one where I'm going through every step from start to finish. It's going to be exactly like what's on the quizzes and the post-tests.
Yeah, because in the post-test it's only says rejected, no rejected.
Yeah, or it might say what's the value of t that you would get in this situation, and it would also say if your observed value of t is this and your critical value of t is this, then do you retain or reject the null hypothesis? So the questions on the final are going to be very, very, very similar to what's on the quizzes and the post-tests. This is too much stuff for a single question. And I would never expect you to know what the critical value was because you have to look that one up. Yeah. Okay, that gets us to the next issue. This is a two-tailed test. And what it means is we're interested in knowing if this sample is different in either way from this one. It could be higher or lower. So for instance, most of the time when people are comparing men and women on something, they're not particularly interested in knowing that women are higher on a particular thing or that men are higher. They just want to know whether men and women are different. And so it's not so important which group is higher, just that a difference exists. And so that's a situation where you do a two-tailed test. And you do a two-tailed test unless you have a very compelling reason to do something else, because this is the standard approach. Now, the issue you have is that there are times when a one-tailed or a directional test is appropriate. So let me show you. So there may be situations, for instance, where you only care if scores go up. So, for instance, so here's t of 0. And an example is like you're only going to make an investment or make a commitment or take a course of action if you have evidence that whatever it is you're interested in gets better, okay? So for instance, if you're going to do a program on, I don't know if you guys remember last year, the Utah Speaker of the House, Becky Lockhart, was trying to make a push to get an iPad or something like that for every student in the Utah K through 12 system. And most people looked at her and said, you're crazy, because she says, oh, it won't cost a lot. And they said, yes, it will. The news today, California or Los Angeles has been doing this. I think they've spent, I want to say, like over $1 billion buying iPads and stuff. And today, they put the program on hold because it looks like something went horribly wrong in the process, which you can expect. But the deal is, you know, you're only going to spend that kind of money, and it can be hundreds of millions of dollars. You're only going to spend that kind of money if you have a really compelling reason to believe that it's going to make student learning much better, right? So what you would do is you get a small group of students, and you'd give some of them an iPad, and you would test them. And you set up this criterion. You say, okay, if their scores, this is where they are to start with, right? If their scores go up, 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 and if they cross this line, then we're willing to make the larger purchase, right? But there has to be evidence that it's going to make a big improvement. If it only gets a little bit better, you're not going to make the purchase. If it stays the same, you're not going to make the purchase. And heaven forbid it gets worse. You're definitely not going to make the purchase. And this, I'll tell you, this is when there's a sort of a trick question in the quizzes that has to do with this. It'll talk about a one-tailed test, and it'll say, let's say that your cutoff is like plus 1.7, okay? Because in a one-tailed test, the cutoff's a little lower, because all 5% is over here. So it's plus 1.7. And let's say that so that's your critical value, right? You can put that as T crit for critical. And let's say your observed T is minus 3.6. You got to be careful, because you look at this, you go like, well, 3.6 is much bigger than 1.7. It's in the wrong direction. It's over here. And so what that says is, well, we were only going to reject the hypothesis if things got better by a certain amount. Instead, they got much worse. So you're not going to do it, right? You just got to watch out that when you do a one-tailed test, you have to make sure that it's in the right, that your sample value is in the right direction. Now, yes?
So we know that it's one tail when it's only positive or negative, right?
Right, and it'll say if a critical value of plus this or minus that, it'll give you just a plus or a minus, okay?
And when they say plus minus, it's double tail.
Correct. And I'll just mention, of course, that this is a one-tailed where you're looking for an improvement. You can also do the same thing where you're looking for scores to go down. So, for instance, if you're looking at the number of kids who get sick or infant mortality, you want that to be really low. And you might institute a program at the hospital to reduce infant mortality, but if it's expensive or if it's difficult to do, you're only going to do it if you have evidence that it's going to really make a difference. And so that's one where you're looking for a decrease.
So when we look at decrease when they're asking us for the negative tail, so the more negative it is, so we don't reject it, right?
Right. Well, let's say in this case, so this is T again, right? And let's say we had a cutoff of minus 1.7, right? So we're looking for something that's negative. In this case, if we got an observed T of minus 2, okay? That would be right here. And that's past our cutoff point, and it's into the region of rejection. And so if we hypothesized a negative value, or which really is sort of the same as saying we're not going to do anything unless we have evidence that it really reduces things, and you get this score, then you would reject the null hypothesis, and you would, and in sort of a decision-making context, you'd say, well, we've triggered the decision. That goes because we set a criterion, it went in the right direction, and it went past that point that we were looking for.
So we don't reject.
We do.
Oh.
Yeah, you see how the X right here is in the shaded region?
Yeah.
That's when you reject it.
Because you want it to get better.
No, in this case, you want scores to get low. Yeah. Again, think of like infant mortality, that's kids dying. You don't want that to happen. You want evidence that some program is going to make that happen less frequently. So you want it to go lower, 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 and as soon as you hit a particular point, then you say that's low enough now that we're going to take this program and institute it, statewide.
And so, 0.3 isn't low enough.
Yeah, like a 0.3? Yeah, that's 0 right there. 0.3 would be right there. Oh, no. The fact that it's past the 1.7, all it has to do is go past this. A 1.701 would be enough.
What's past it? Yeah,
I didn't understand what you
sorry, you were
reacted, so.
saying that for something like the iPad, the example of the iPad,
Mhm.
if the students get better and better and better, they're going to affect the program.
Right.
And with the death of children,
Mm-hmm. You want that lower, lower, and lower.
lower and lower. So the more lower it goes,
Mhm.
-2 is going to be very low. It's lower than
It's lower than our cutoff. Mm-hmm.
So we accept the program? Or
Correct. We reject the null hypothesis, which says that the program has no effect.
Oh,
The null is that the program does nothing.
Oh, okay.
And once we get down to here, we say, we no longer believe that the program does nothing. We believe that the program produces the intended decrease.
Oh, okay. So we reject the,
Mm-hmm.
the idea that the program doesn't work, but
Yeah.
we accept
Now, let me write the hypotheses here, okay? When you're doing a one-tailed where you're looking for scores to go up, your hypotheses look like this. You still write it in terms of all these population means, right? So this is the sample, the population mean that the sample came from, and this is the population mean of your comparison or control population. We write it slightly differently. Previously, here, look. When we did it right here, we used equals and not equals, right? Because we were interested in it going either way. Well, here, only one direction matters. And so what we do is you start, the alternative hypothesis is usually the one that you're interested in. So here, we want to see an increase. So that means that this one is decrease or equal. And so what you're saying here is the iPad thing, you say, well, if scores stay the same, we're not going to make the purchase. And if scores get worse, we're not going to make the purchase. We have no evidence that there's an improvement greater than chance. Down here, however, it goes the other direction. This one, we're interested in things getting lower. So we go like this. Again, it's easiest to write the alternative first, because that's the one that you're interested in. And then the other one just goes in the other direction or equals. And if it's this value, then we reject the null hypothesis, which says that this sample mean is higher or equal to the control population. And it's not. It's lower, which is what we were looking for. By the way, is it one of you who contacted me about whether I would offer extra credit for coming to this session? Because I offer extra credit for meeting in a study group, right? And I got a question of whether this counted as a study group. And my response is probably not, because a study group, the idea of a study group is that you actually might be in a position to teach somebody else something. And that's not probably going to happen here. It's mostly going to be me talking to you. And so I said, probably not. But you know what? I think if you guys want to count this as your study group, I'm happy to do that. Okay? All you have to do is you get on Canvas and you go to the extra credit things and you click on submit response and you say, I did it. I'm not even going to ask where it was or with whom or when. You just say, I did it, and you get credit. And since you guys have been to all 3 of them, and you've been to 2 of them, and you've been here, yep. So get yourself some credit, okay? All right, that's t-tests. shall we talk about the analysis of variance? Or let me rephrase that. Do you have questions about the analysis of variance? That's chapter 10. Okay.
Oh, but first, could you give us which of the formulas are going to be on the test? All the formulas we're going to use on the test? Or?
Any formula that's on the study sheets that I put on Canvas can appear on the test. Although I will mention, those study sheets were made for formulas that could appear on any of the 3 exams. Because there's 1 or 2 formulas that show up on exam 1 or 2 that do not show up on the final. But don't worry about it. They're all good to know. And besides, there's really not that many. There's not that many. I mean, you need to know how to calculate the mean. You need to know how to calculate the interquartile range. You need to know how to do the median for even or odd numbers. You need to know how to do the standard deviation or the variance, and those are the most complicated ones we have. You also need to know how to calculate the standard error and how to do z-scores for individuals and samples, and also how to take z-scores and convert them back to x-scores. And the last thing you need to know how to do is to take a regression equation and compute a predicted score. A predicted score. I can show that to you in a minute, okay? Just ask me when we do chapter 11. And I think that's it in terms of formulas. And the 3 study sheets that I have linked on Canvas has all of those. But you have to look at all 3 of them at once. Just remember you can't take them into the exam with you. I know. Although, do you guys know this? I have some students who I thought, well, that's smart. They take their study sheets with them while they're waiting in line. They are studying up until the second they get the exam. They throw it away, and then they immediately pull out a blank piece of paper and write it all down. So, you know, it's sort of like they just have to remember it for 10 seconds and put it down. I thought, well, of course, that's allowed. That's allowed because you can have scrap paper. And you can study up until they give you the exam. So study, then switch it over as fast as you can before you forget. All right. Analysis of variance. What questions do you have? Should I institute my 30-second lull policy? If there's no question for 30 seconds, we're done for the night.
Oh.
That's how I get home sooner. I can tell you're looking furiously for something. They have an iPad built into the desk up here. They could have done that with a $100 touchscreen instead of a $500 one. Yeah. If you can.
Okay, on quiz 10.2, the first question, it says the analysis of variance is useful if you want to, and then it gives you some options. And I just kind of got confused about exactly what situations to use the
Okay,
analysis.
so this is The quiz for Chapter 10, second quiz, first question. The analysis of variance is useful if, and what are the choices?
To compare the mean income of men and women.
Okay, compare the mean income, so comparing the means of two groups. Okay.
Compare the number of men and women in different political parties.
Okay, let's put this in. Means for men and women. Second,
Compare number of men.
in political parties.
Yeah.
Mm-hmm.
And then test the change in scores for a group of people before and after an intervention.
Mm-hmm.
And then compare the mean income of people in several different jobs. But now that I understand the t-test a little better, reading over like 2 and 3 maybe, I don't know, like that kind of connects to the t-test more to me.
Okay.
So
The first one, you're comparing the means for men and women. That's comparing the means of two different groups. Now, I'll let you know, you can use the analysis of variance for that. It is possible to compare two sample means with the analysis of variance. However, it is much more common, and the reason this is not marked as the correct answer is because you would usually use a t-test for that, and a two-sample or independent samples t-test. This one right here, comparing the number of men and women in political parties, that's frequencies. You're counting how many people there are, and you're not getting a mean. And so that actually is an example of what we do in Chapter 12 with chi-squared, because that's the only inferential test that you use for frequency data. This third one, where you're looking at changes over time, that would be the repeated measures t-test. Now, that being said, there is a version of the analysis of variance that deals with changes over time, but it actually is much more complicated, and it's much easier to deal with the t-test. This one right here, where you're comparing the means of people in several different jobs, that is a classic analysis of variance situation, because you're comparing the means of more than two groups. So you can't do that with t-tests. You can't do it with chi-squared because you're looking at means, not categories. You're not looking at changes. So you're comparing the means of several groups. That's analysis of variance. That's when you would use that. So that's why this is the correct answer for that question. You can also, there are two situations where it's really common to use the analysis of variance. The first one is where you're comparing the means of several different groups, where the groups are all categorized on a single variable, like job category. And you can have lots and lots of categories. Or you can talk about time to graduation of people in different majors. You got lots of different majors that you can list, or different colleges. Lots of choices there. Or I'll tell you one that's interesting is to look at the average level of state funding per student for each of the colleges and universities in the Utah State higher education system, because UVU gets less than anybody else. Yeah, oops. And the other situation, and that is called a one-way or a one-factor analysis of variance, and that's because you have several different groups, but they're all categories on the same variable. You can also do an analysis of variance with more than one factor or more than one categorical variable where you're categorizing people. So the classic example of this, and I may have used this example in the book or the video, I can't remember. But in my field, social psychology, I remember seeing a talk a couple of times by a guy who has been studying racial prejudice. And he talked about this situation, about the level of discrimination people say they experience in their lives. And he categorized it in two different ways. He had men and women, and then he had white or European American and black or African American, okay? And what he was saying is, everybody knows sexism is real. Men get paid more for doing the same job, even when there's the same level of experience, same level of education, same level of everything. there's still an overall difference. Men get paid more. He says, so women experience more sex-based discrimination than men do, right? He says, also, common knowledge and the research supports the fact that African Americans, Black Americans, experience more racial discrimination than white or European Americans do, right? He says, therefore, oh, by the way, and the way you would write this is, well, let me finish it off. He says, therefore, you would expect that black women would experience the most discrimination of all. He says, that is not the case. He says, it is far and away black men. He says, so on the discrimination scale, if we're doing it like on a 0 to 10 scale, this is going to be like an 8 right here for black men. And this might be a 6 for black African American women. Whereas for white or European American women, it's going to be like a 4, and for white or European American men, it'd be like a 2. Okay? Now, here's what's interesting about that. Is first off, that I did not draw my numbers well. But because what you do is you average going across. So we have 8 and 2 together is 10. So we have an average there of 5. And 4 and 6 together is 10, which is 5. And I should have made it so this number was bigger. So that this number was like a 6 and this number was a 4. Okay, so I messed up. But this way, going down, 2 and 4 together is 6, so that's an average of 3. 8 and 6 together is 14, which is an average of 7. And so you can see there's a big difference right there, right? This is called a main effect. And it tells you that the factor or the categorical variable of race or ethnicity makes a difference on the level of discrimination people experience all on its own without knowing whether they're male or female. That is sufficient. And here you have Black Americans or African Americans experiencing more discrimination. Now, if I did my numbers differently, these numbers would, work out so that that this number would be like a 6 and a 4. Okay, that women experience more discrimination than men. But the big thing here is the fact that here the number goes up, but here the number goes down. It goes in opposite directions here. And so what it says is, if you want to know the effect of race on discrimination, you need to know whether the person is male or female. Similarly, if you want to know the effect of sex on discrimination, you need to know the person's race, because it makes a difference. Okay? Because the pattern flips around. And that's called an interaction. And an easy way to look for interactions, this, by the way, is called a 2-by-2 table, because you have one factor over here that's an independent variable. People sometimes call them independent variables, but that's really only when you manipulate the variables. And you don't manipulate and assign people to their sex or their race. So we have one predictor variable here. It's called a factor, and it's got 2 levels or 2 categories within that factor. So this is called a 2, because there's 2 rows, by 2, because we have another factor here with 2 levels. So a 2-by-2. And if you want to, you can look for what's called an interaction between the 2. And the easy way to do that is to average them on the diagonal. So 2 and 6 together is 8, and that makes 4. And 8 and 4 together is 12, and that makes 6. And so 6 is greater than 4, and so that would tell you that there would be an effect on the interaction here. And that's sort of just a numerical confirmation that shows, the pattern flips around depending on which side you're on. So that's, and by the way, this 2-by-2 analysis of variance, I've said this about 1 million times. This is the bread and butter of experimental psychology. In my field, which is experimental social psychology, you get so many of these because this is the kind of analysis that you use for testing causal theories most of the time, or testing a moderated relationship. This is the one you use to see if something qualifies something else. This is a very common one. Yep. So that's when a very common situation for using the analysis of variance. By the way, you would get 3 results from this. There are 3 separate inferential tests, and you get the statistic that you're getting is F. That stands for Fisher, for Ronald Fisher, the guy who invented this test. And you would get, if we call this one factor A, and if we call this one factor B, then what you have is an F test for factor A. You also have an F test for factor B. And then you have a third F test that is the interaction of A and B. So that's 3 separate inferential tests that happen when you do this kind of procedure. And for each one of them, you'll get a value of like, let's say 4.60 and 12.10 and 18.03. And then each of these, so these are test statistics. It's in the F distribution. And the F test is always positive. It starts at 0 and it goes up. Because variance is always positive. It starts at 0. You can't have negative variance. It starts at 0 and it goes up. So the F test does the same thing. And so for each of these, you would also get a p-value, which is the probability of getting an F test that big through random chance variation if the null hypothesis is true. And in this case, all of them would be pretty small. 0.03, 0.005, 0.0001. I'm making them up, right? Understand, these are made up numbers. And in each case, you're looking to see whether the p-value that you get is less than your alpha, and your alpha is usually 0.05. And so you check, yeah, that's less than 0.05, that's less than 0.05, and that's less than 0.05. So all 3 of these would be statistically significant effects. Okay. Now, it is often the case, the most interesting one for experimental psychologists is you may have it that there's not a main effect here and there's not a main effect here, that the means are like 5, 5, 5, 5. Here, let me just show you a quick situation. The easiest possible version of this is when you get a pattern that's like this. Because that's an average of 5, that's an average of 5, that's 5, and that's 5, and the grand total is 5. So there's no difference by rows, there's no difference by columns, but there's an enormous difference in the interaction. And this is one that tells you, it's the interaction that matters here. And most of the time, that's what people are interested in anyhow. And so the fact that this one is significant and these are also, these 3 operate independently. And so I have pictures of lots of different bar charts that show maybe this is that you got a main effect on A but not on B, but you have an interaction and so on and so forth. That can happen here. I'll show you just one more kind of effect. And this is one where people would say, you just want to look at the interaction. Another thing that can happen is you get a funny little, you can get something that's almost like this, 0, 0, 0, 10. So it's 0, 5, 0, 5, and the overall is 2.5. And in this case, yeah, you might have a significant effect here because the 5 is bigger than 0 and the 5 is bigger than 0. And so you may have a significant effect for each of the factors, but you would ignore it. And the reason for that is because this is driven entirely by the interaction. It's just the interaction that matters. I can give you an example of this. Well, I mean, if you want one from chemistry, you can sometimes have chemicals that are totally fine on their own. But if you combine them, you have a major problem, right? But in psychology, an interesting example is schizophrenia. Now, this is not my field of expertise, so I'm just telling you what I've been told. And that is, my understanding is that for a person to develop schizophrenia, two things have to simultaneously be true. Number one is they have to be born with a genetic predisposition. There's a genetic risk that has to be there. And if it's not there, you can't get schizophrenia. You can get lots of other horrible things. Things can still go very wrong, but it won't be schizophrenia. But that genetic propensity is not sufficient. You also have to have triggering events. Okay? And the technical name for this theory is the diathesis stress model, where the diathesis is the genetic ability to get the disease, and the stress is the event. And in the case of schizophrenia, it's usually horrible abuse that triggers this tendency. And so the idea here is, if you're looking at schizophrenic symptoms, well, this is people who, have the genes, and this is, do you have the genes? No, yes. And do you have the event? No, yes. If you have neither one, you're not going to show the symptoms. If you have one but not the other, you're not going to show the symptoms. You might show other symptoms. I'm just talking specifically about schizophrenia. But if you have both of those, then boom, you get it big. So that's a simplified model. Schizophrenia is actually a very complex and difficult thing, but that's a simplified idea of where you might get this kind of interaction, where you have two necessary conditions, neither of which is sufficient on its own. Okay. Lots of 2x2s. Any other questions about analysis of variance? I'm going to assume we're done on that one. Let's talk about any questions you have on Chapter 11, which is correlation and regression. Giving the camera something to focus on. Looking it up, looking it up, looking it up. This is the exciting part of the video for the people who watch it tomorrow. Yeah. For regression, because I talked about them earlier for t-test. Okay, for correlation. Well, let me bring out an earlier chart. This is where I gave an example of a non-directional hypothesis test for a t-test. And what I said is, in this case, you're looking for a change in either direction. And the way I worded that was by either the population means are equal or they are not equal. Right? And you can contrast that with a directional hypothesis, where, for instance, you only care if they go up. And so the alternative hypothesis says that the population mean for the sample is greater than the population mean for the comparison group, whereas the null is the opposite of that. It's less than or equal to. And then down here, there's a situation where we're only interested if they go down. And so there, I put the less than because I'm only interested if the population mean that the sample came from is lower than the population mean for the comparison population, and this one is the mutually exclusive complement to that. Now, you can do the same thing with correlations, all right? That's exactly what that is, one-tailed and two-tailed. In correlations, what it's going to be asking is in correlations. Okay, let's do this. Let's draw, whoa, very fuzzy. And we're back, okay. Let's draw a quick scatter plot. So correlation, you're going to have two variables, x and y, right? And you might be looking to see whether there is a positive correlation between two variables. In that case, the way you write it is, our hypotheses always come in pairs. Now, technically, because hypotheses are always written about population parameters and not sample statistics, you need to use the Greek rho, which looks like a p, looks like a lowercase p. But on the final, the person who wrote the final does not use rho. This is what rho looks like. It looks like a p without a cap and doesn't quite close. But rho is the proper one, but on the final, they just use r for correlation. Interestingly, R is actually short for regression because correlation and regression are extremely closely related. And so the question here is whether R, if you're interested in whether it's positive, you'll say, okay, R is greater than 0. And then this one is R is less than or equal to 0. So that's if you're interested in a positive pattern. Positive just means uphill, right? So there is an uphill pattern. The null hypothesis generally is that it's totally flat, that it goes straight across like that. But instead we have it angled like that. So if it were totally flat, that would be a correlation of 0. That would not trigger this, right? Because we need it to be significantly greater than 0. And if it were downhill in the other direction, it wouldn't trigger it either. It's only when it's a positive association. That's a one-tailed hypothesis test for correlation. And you could flip it around the other way where you're only interested in a downhill relationship. Okay. A good example of this is, truthfully, is the association between things like education and income or education and well-being. I imagine you know that there is, in fact, a positive association between education and income, that people who get college degrees generally, not always, but generally make more money than people who don't get college degrees. And usually, people who get graduate degrees make more money than people who have bachelor's or associate's degrees. There's a pretty strong pattern overall. There are always exceptions, but that's exactly what they are. They are exceptions. A more interesting one is the association between education and well-being. Sort of like happiness. And there is a stronger pattern there, where the more education a person has, the happier they are, the higher their well-being. And that's going to be tied into the fact that you're not in some cruddy dead-end job that you hate, and that you also make enough money to take care of things. Do you guys know about the research on income and well-being? I'm going to go slightly off topic for just a moment, because it looks like this. This is true both at the individual level and at the country-by-country level. And it kind of looks like this. If this is money on the bottom, and this is well-being, here we go, on the side, the pattern is kind of like this. And so here's what it is. It's curved. There's a cutoff point. And let's say that cutoff point is about right there. Okay? And there's a cutoff point below which there's a very strong association between income and well-being, both at the individual level and at the country-by-country level. And what this means is that being poor really sucks. Because if you're really poor, you may not be able to, live inside a building. You may not be able to get food. You may not be able to take your kids to the doctor. Horrible things can happen. You may not be able to get clean water. If you're really poor, bad things happen, and they happen a lot most of the time. But once you reach a certain point, and this point is at which you have enough money to pay for the things that you need, then it sort of flattens out. And there's no longer any strong association between income and well-being. And that doesn't mean that the more money you have, the less happy you are. It just means we just can't predict anymore. You might be happy or you might be less happy, but there's no reliable association. But there's a very reliable association below a certain level. And this, of course, is going to vary from country to country because of the cost of living. But I can tell you what it is in Utah. For a family, this is family income, it's somewhere in the vicinity of $40,000 to $45,000 a year. I know that's not a lot for a household income, but the point is it's enough. It's enough to pay your rent. It's enough to get your food. It's enough to heat your house and go to the doctor. It's enough to do a number of things. You can live on that. You're not going to have a fancy house and a fancy car, but the funny thing about it is after that, there's no more reliable association. You'll have nicer stuff. There's no doubt about that. And you'll be able to take that trip to Europe instead of taking that trip to Wendover. And there's things that go, but that does not reliably determine whether you're going to be happy or not. So that's an interesting one. And so an important thing here is college is going to help you get past this cutoff. Okay? It's hard to make that much. Yeah. I was going to say, actually, a plumber makes more than this. Plumber makes about $60,000, $65,000 a year. And truck drivers can make more than that. If you have a consistent, steady employment, it's a funny thing. Anyhow, I just thought I'd share that with you. Yes. Yes. No, it cannot. R is bounded. R has a limit. The absolute value of R is somewhere between 0 and 1. It can be plus or minus, but that only indicates the direction. The 0 to 1, is affected by the strength of the relationship. This just indicates direction. So it's not possible to have an R of 1.1. And it's very rare to have an R of exactly 1 or negative 1, because that means that every single score is uniquely associated with one other score on the other variable, and that usually only happens, that only happens when your plot looks like this, or like this, when it's a totally straight line. And usually that only happens when the thing you're talking about on the two dimensions is the same thing. So for instance, my silly example is your height in inches and your height in meters. Because they're different scales, but it's still measuring your height. And so it's going to be this one-to-one relationship. Most of the time, though, it's going to be more like this. And so it's going to be, I'll tell you, in the social sciences, a correlation of 0.3 is usually a big deal, even though that's closer to 0 than it is to 1. But that's usually considered a reasonable association in psychology. lot of things have multiple meanings, but R I only think of in terms of correlation. Now, there is one thing that can go to you can go to an infinite decimal places, and you can have something like R is equal to 0.78, and then you can give a p-value, and the p-value might be like 0.000001. You can have an infinite number of decimal places there. Okay, other test statistics. R is the only one that's bounded on both ends. A t-test can go to infinity in either direction. An f-test can go from 0 to infinity. A regression coefficient, which is related to R, a regression coefficient gives you the slope of the line, and that's usually written with beta. That can be plus or minus infinity. And another statistic that we talk about in chapter 12, chi-squared, that also can go from 0 to infinity. Yeah, that's chapter 10. We're in 11 right now. Don't worry, though. You can look at it on the video tomorrow. But correlation and regression. What else?
In the test, it's going to ask us to use the ANOVA, or?
It's not going to ask you to calculate an ANOVA.
Oh, okay, just the question.
Here, it's going to be something along the lines of, assume a researcher has done an analysis of variance, and they get an observed F of 7.3. If they are using a critical value, so that's F observed, right? If they're using a critical value of F is 4, should they retain or reject the null hypothesis? You tell me. No, reject. Yeah. Because remember that our critical value here, by the way, F is always positive, right? So the critical value on the F test looks like this. Because it's always positive, it looks like that. This is 0 right here, and this is going up to infinity. And you're going to check off just one side, because it can only be one-tailed. And so that's 4, right? And what they're saying is we got a value of 7.3, which is going to put it like, out here somewhere.
So the point that we have to go is the critical point. That is our point.
That's the cutoff point, yeah. And if it goes past that, then you reject the null hypothesis. I'm glad you're asking this because there's a lot of questions on the final about this. I mean, because think about it. The hypothesis stuff, the accept, retain, reject stuff, comes up in chapter 7, 8, 9, 10, 11, and 12. All of those chapters include that kind of question, so it comes up a lot. So you have to be very comfortable. Now, I'm going to tell you one other thing. When you have a question about retaining or rejecting the null hypothesis, there's 2 ways that it can be phrased. One is in terms of the test statistic. And in that case, you have an observed statistic, an F value of 7.3, and you have a critical value. That means in that statistic, like F or like T or whatever, if it goes past this, then we reject the null hypothesis. So you can word it in terms of the test statistic. And in that situation, you're almost always looking for a bigger value. Okay? However, the other way that you will see it is worded in terms of probabilities and alphas. So the way that would go is they would say a researcher conducts a test, blah, 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 and they get a p-value, or just p. of 0.04. And if they are using an alpha, whoops, that's a bad alpha, of 0.05, that's the, remember, what the alpha is how much of the null hypothesis distribution are you shading off as as false positives that you're willing to accept. You have to shade off some of it because it is infinite in either direction. You have to choose some of it or you'll never reject a hypothesis. And the standard is 0.05. Now, ready? So this is the other way to word it. It's in terms of p-values. So if a researcher does a test and they get a p-value of 0.04 and they're using an alpha, this is a criterion here. If they're using an alpha of 0.05, you tell me, should we retain or reject the null hypothesis? This one we reject. I know. Here's the deal. Ready? This one, we're looking for bigger values. With a test statistic, you're almost always looking for bigger values. You have a criterion, that's your cutoff, and you're looking for a bigger value, something that's more extreme than that. With a p-value, however, you're looking for smaller values because what a p-value is what's the probability of this happening by chance? And you're saying, well, it needs to happen less by chance, less than 5% of the time. That's my cutoff. That's my alpha. It says if it happens by chance less than 5% of the time, I'm going to imagine that it's probably not chance, that it probably indicates an actual difference. And this p-value right here tells us that we get a test statistic this big or bigger by chance 4% of the time. If our cutoff is 5%, it has to happen by chance less than 5% of the time, and we get a sample value that happens 4% of the time. 4% smaller than 5%, we reject the null hypothesis because we said it has to be rare, and it's more rare than we said. Now, I'm going to complicate it. Ready? Instead of an 0.5, let's say we used an 0.1, because that happens also. So people sometimes use a smaller alpha. And then what that is they want a smaller probability of a false positive. It'll happen, for instance, a lot of medical research. Now we retain. The sample value has not changed. All it is that we've changed our criteria. And a good example of this from the real world is, well, I can give you two. My favorite example is from the legal world, and I probably talked about this one last time. I talk about it all the time. You guys may not be old enough to remember the O.J. Simpson trial. Some of you. O.J. Simpson, an American football player who was accused of killing his wife, Nicole Simpson. This happened about 20 years ago. And it was one of the most bizarre, because everybody loved O.J. He was this fabulous, wonderful guy. Everybody loved him. Sort of like Michael Jordan. Everybody still loves Michael Jordan. He has not fallen yet. And like everybody loved Bill Cosby up until like 3 weeks ago. And so everybody loved O.J. And then people said he killed his wife, and he got involved in this really bizarre 55-mile-an-hour chase on the freeway. His friend was driving this Bronco at the speed under the speed limit, and they had like 14 police cars and helicopters following them, but he's going down the freeway. Well, what happened is it went to trial, and of course, and it's a situation where sort of like the common knowledge was that of course he did it. How could he possibly not have done it? But he was acquitted in the criminal trial. He was not convicted of murder in the criminal trial, and that trial went on forever. Then, as soon as the criminal trial was done, now a criminal trial is to determine whether a person committed a crime, right? But it was followed up immediately by a civil trial. A civil trial is to see if you have performed some sort of injury to somebody else in terms. Usually, it's money, right? And in the civil trial, he was convicted almost immediately. And so the immediate question is, wait a second. If he's off the hook on the criminal trial, how can he get convicted in the civil trial? And the answer is very easy. If you guys are familiar with the American legal system, we have different standards of evidence for those two kinds of trials. In a criminal trial, a person can only be convicted if the jury is certain beyond the shadow of a doubt. And that means that you have to be like 99.9% certain that this person actually did it. If you're 99.8, you do not convict them. You have to be totally certain that it happened, beyond the shadow of a doubt. There's just like no doubt in your mind that it happened. And there was a shadow of the doubt in the jury's. But in a civil trial, you simply have to have what's called a preponderance of evidence. And that means you have to be 51% certain. And so it's sort of like his guiltiness was not different. You know, say in both cases, say for instance, the jury was 95% certain that he did it, but we have different cutoffs. In the criminal trial, it's 99.9, and his 95 did not meet that. But in the civil trial, it's only 50. And he went way past that. Another analogy for the social sciences, are any of you guys familiar with the BESC Depression Inventory? It's a very common questionnaire for assessing depression. It's a self-report questionnaire. People fill it out. And it's only like 20 questions. And if you look at it, you can say, well, yeah, that's what exactly, like, are you sad? But you get a score on the BESC Depression Inventory, and there are two cutoffs. And basically, you can think of them as outpatient and inpatient. So let's say, I don't know what the cutoffs are, but let's say like 15 is the outpatient cutoff. So a person who has a score of 15 or higher is seen as depressed enough to need therapy. And then there's another cutoff at like 20 or 21 or 25 that's inpatient. And it says this person is so depressed, we really can't let them go home. We're going to have to, keep them here under supervision and take care of it. And so it's sort of like depressed and really depressed. And you can talk about, is a person depressed or not? Well, that's a hard question to answer because that's something that's continuous. It's a continuum that people range up and down on it, and it shifts from moment to moment and day to day. And so the idea that, a person may have a 16, it's like, well, are they depressed? Well, they exceeded the outpatient cutoff. But are they really depressed? Well, they're not inpatient. So there's some sort of in between there. And the trick, of course, is if you were to test them a week later, you may get different results. Now, the people who develop tests like this do their best to make sure that these results are not susceptible to momentary influences. It's serious work. But anyhow, thought I'd just share that with you. Yes.
That's it. The graphic for the second one is for the p-value. It's a left skew, right?
Oh, okay. P-values ignore the direction. Because all they're saying is, what's the probability of getting something like this by chance? And it's sort of, you can calculate a directional p-value. You can. It's not done very often because almost always what it is if you're doing a directional test, you start with the p-value and then you immediately translate it to the critical value in the test statistic, and then you just run with that one. Because the direction matters and p-values don't indicate direction. They indicate really how far away are you from the mean. So I'd say that these are sort of inherently non-directional because there's no plus or minus on them, right? But these are directional, or can be. F-test is not, but the t-test is. Okay. I'm going to show you one other thing that you didn't ask me about from regression. You need to be able to calculate a predicted value. It's actually not hard. It's very simple algebra. Very, very simple algebra. You guys may remember, like in high school or junior high, learning how to graph a line, where x is this is x, this is y, and we're getting a line here, and m is the slope of the line, how angled it is, and b is the y-intercept, where it is, what value of y it has when it crosses 0. Well, in statistics, we don't usually use this formula. That's common in geometry. We usually flip it around a little differently and write it like this. Y is equal to b0 plus b1 times x1. And this is the intercept, and this is the slope. Okay, b is the symbol for a regression coefficient. That's what it's called. The slope and the intercept are both coefficients. It's just a number that you multiply something by. And the reason we use 0 and 1 is because it's possible to have more than one variable, and so on and so forth, right? You can have lots of predictor variables. But we're not dealing with that. That's called multiple regression. We're just doing this simple version, which is called bivariate or two-variable regression. No, it gets into higher dimensions. If you have bivariate describes a line. If you have two predictor variables, it describes a plane in a three-dimensional space. If you have four variables, if you have three predictor variables, I think it describes like the surface of a sphere it gets crazy. You don't visualize it anymore at that point, right? So it's not lines, but it's pretty easy to deal with because you guys know, if you want to predict your income, here's the average, start with this, and then for every year, add this many dollars, and for every year of education, add this, but every time you've gone to jail, subtract this much, and so on and so forth. And you just kind of bump it up and down as you go. That's if you're doing what's called just a totally linear one where you don't have interactions between things. Interactions are very common, but they're very difficult to deal with. Intercept and slope. So, for instance, you would use the regression, and you would do a calculation to get the intercept and the slope. I'm not going to ask you to do that. We're just going to tell you the intercept and the slope. So let's say, for instance, that b0, which is the intercept, is equal to 6, and that b1, the slope, is equal to minus 2. Okay? Yeah, so here's what I'm going to do. And say, so if a person has a score of 2 on x, then what will we predict their score would be on y? So here's how it works. Ready? We've got b0 plus b1 times x1. So we go like this. b0 is 6. The slope is negative 2, and their score on x is 2. Like that. So just work through it. Negative 2 times 2 is negative 4. When you add a negative number, that is the same as subtracting. 6 minus 4 is equal to 2. And I'm going to put a little hat on that. In French, that's a circonflexe, and in English, it's a caret. Spelled the same way like the carets in a diamond. And it's on the keyboard over the 6. And that means a predicted value. And so what this says is if a person's score on x is 2, and this is the intercept and this is the slope, then we would expect them to get a score of 2 on the y variable. It's coincidental that these are the same. Normally they won't be. So let's do it again, except this time with a score on x of minus 3. You tell me what the predicted value of y is. When this is the intercept, this is the slope, and this is the x value that we're dealing with. So run through the equation. Yeah, -3 when x equals.
12.
Okay. All right. You're probably right. Okay. I'm going to pretend you guys all worked on that. Here we go. Y is equal to the slope, the intercept, which is 6, because I've got that right here, times the slope, which is -2, times x, which in this case is -3. All right?
That is plus,
What's that?
6 plus.
No, that's times. Plus, geez. Yes. Thank you. 6 plus -2 times -3. Well, a negative times a negative is positive, right? And so that is actually +6. And 6 plus 6 is 12. So if a person has a score of -3 on x, then we would expect them to have a score of +12 on y. Doesn't mean that's actually what they're going to have. It's just what we expect them to have. And so, for example, let's talk about a negative association. I know some actual data that looked at 5th grade students and assessed them for symptoms of ADHD. So it's a scale where low numbers mean very few symptoms of ADHD and high numbers mean you've got a lot. And then they compared that to their performance on an academic test. Not surprisingly, it looked like this. Kids who had high symptoms of ADHD tended to get worse grades. Okay? Now, let me just mention something really important. This is a correlation. And one of the things that if you study research that gets hammered into your head is correlation does not imply causation. Correlation and causation are very different things. So just for a moment, the fact that a person has pretty severe ADHD does not mean they're stupid. They might test poorly, but there's a lot of things that ADHD is going to, there's a lot of reasons that a person with a lot of ADHD symptoms why they're going to test poorly that has nothing to do with intelligence. Testing situation is going to be a big one of them, right? And that's why we make ADHD as one of the protected conditions under the Americans with Disabilities Act. And that's why a person who has recognized ADHD is legally required to be tested in situations that suit them, so they can actually show how smart they are, as opposed to showing how well they can test under stressful situations or distracting situations. That's a different thing. I can give you a really easy example of this. I mentioned it before. Women make less money for the same job than men do. It's a fact. And what's weird is it's in almost any profession, even jobs that are typically run by women. Guys almost always make more doing the same thing. And, okay, ready? We all know it's not because you have 2 X chromosomes. That's not what causes the change in pay. What it is that gender is associated with a million other things that do produce the association in pay. And some of them might make sense, but some of them are just predictors cues for straight-ahead sexism. And so it's there. But I think we all agree that it's not that there's some sort of like biological imperative that requires that you get paid less if you're a woman. There's other things that affect it that have nothing to do with it. So a person's sex might be a good predictor of pay, but it's not a cause. You don't have to have a causal relationship to use something as a predictor. And an interesting place where you see that, for what it's worth, is in internet marketing, where they look at, the things that you click on and how long you look at things, and you say they do not have to have any causal theory at all because they have so much data, billions of observations, that they can predict almost perfectly what's going to happen without having an actual theory. Because they say, well, we know that 99% of the time when a person does this, this, and this, and this, that usually gets followed with this and this. So anyhow, it's a different situation. If you want to make a lot of money with statistics, and actually this is fun stuff, but internet marketing is a huge, huge place. Or really anything on the internet. Because you actually can use statistical models to predict behavior very well in those situations. You guys may be interested to know that you can actually use a person's Twitter tweets as an indication of both depression and psychopathy. He's being a psychopath. I hasten to add, psychopath does not mean a violent killer. It's not even antisocial, because an antisocial person is antisocial personality disorder is sort of a different thing. That's where you're actually trying to hurt people. A psychopath or a sociopath just wants what they want, and they're willing to lie and cheat and steal to get it because they don't care about other people. And I'll just mention that a person who is willing to lie and cheat and steal with no remorse tends to do very well in certain professions. Sales and politics are two of them. Now, you do not have to be a sociopath to do well in those things. And truthfully, if you are a sociopath, you might get found out eventually because you'll probably do something horrible along the way. But if you can lie and cheat and steal without feeling bad about it and can do it with a straight face, you're going to get away with more things. So you can tell a little bit by Twitter. Fascinating, huh? Yeah. Back on topic. Okay, there is a situation in which that is the case, and this is an interesting one. It's when you are doing regression with standardized scores, with z-scores. So let me show you how that works. Instead of trying to predict y, what you're trying to predict is a z-score on y. Okay? And when that happens, the equation is a lot simpler. You don't use their x score, you use their z-score on x. And the only coefficient is the correlation coefficient. There's no intercept. The reason for that, by the way, let me see if I got, it's because the intercept always goes through, let's say that's the mean of x, and this right here is the mean of y. The intercept always goes through the point defined by the mean of the two variables. But remember, the mean of a standardized variable is 0. And so when you're dealing with zx and zy, the mean of both of those is 0. So all it means is that the regression line goes through the origin. It goes through the 0, 0 point on the chart. So you don't have to include that. And the slope is the correlation coefficient. So, ready? Let's do a couple of things here. Let's say, for instance, that a person has a z-score on x of 2. That's a 2 as opposed to a z. And what it means is that they are 2 standard deviations above the mean on x. All right? Now, let's say that the correlation between between x and y, and you can put that right there. You can put x and y right there if you want to. You don't need to. Let's say it's negative 0.5. Remember, correlations are bounded. They cannot go below -1, and they cannot go above +1. And they're almost always closer to 0. So if a person has a z-score on x of 2 and the correlation between x and y is 0.5, then what is their predicted z-score on y? That's a question you get to answer. Yeah, calculate it. Correlation coefficient, -0.5, times z-score on x of 2. -0.5 times 2 is -1. So if a person has a z-score on x of 2, we would expect them to have a z-score of -1 on z, on y. Okay? The correlation coefficient is bounded. It can go anywhere. Okay, ready? What I said earlier is that r, the value, the absolute value of r, ready? It goes from 0 to 1. And the direction of r can be positive or negative, which means that it goes from -1 to +1. But -1 and +1 are both perfect linear relationships. They're just in different directions. So there's that. Okay, ready? Let me give you an interesting little trick question, because I think this shows up on one of the quizzes or post tests. Let's say we still have a z-score on x of 2, but let's say instead of the correlation being -0.5, let's say the correlation is 0. What do we predict their score on y to be? Yeah. In that case, r is 0 times 2. Well, 0 times 2 is 0, right? And by the way, do you guys remember what it means when a z-score is 0? It's the mean. It's the mean. And what that tells you is that if there is no association between your predictor variable and your outcome, because the correlation is 0, if there's no association between the two, then you just predict the mean on the outcome variable. Right? So, for example, if I'm trying to predict your income 5 years after graduating, and I either know nothing about you or I only have information that's totally irrelevant, then all I can do is predict, well, what's the average for 5 years out? And that would be my prediction. Until I have some information that actually is correlated with that, I stay with the average. And then once I have correlated information, then I can start bumping up and down a little bit. I want to mention one other thing about this particular equation right here. This correlation also works into regression to the mean. You remember regression to the mean? The idea here is that people who have extreme scores on one variable tend to have less extreme scores on another variable. Or it comes from the original research on the heights of fathers and sons. Very tall fathers tended to have sons who were tall but not as tall as they were, and very short fathers tended to have sons who were short but not as short as they were. In other words, the height of the second generation returned or regressed a little bit towards the average, the mean. That's regression towards the mean. And you can see how that would work with this equation, because the only way that the scores on y are going to be as spread out as the scores on x is if the correlation is a perfect negative or positive 1. That's the only way it's going to happen. Anything less than that, and since a perfect plus or minus 1 correlation almost never happens, let's say your correlation is like 0.8. Well, then it means that the variability is, so if a person has a z-score of, 2, right? That means they're 2 standard deviations above the mean on x. It's going to shrink a little bit because you're multiplying it times a number that's in between 0 and 1. So it's going to be 1.6 as opposed to 2. So you're going to predict less variation. It doesn't mean that they're always going to be less variable. You know, people can have children who are taller than they are, or, you know, that happens, but most of the time things tend to vary, get a little closer that way. We have 12 minutes left. Chapter 12.
When it's means, I see what it was, but I have difficulty with it.
Okay. It's actually, there's actually an easy answer to this. Ready? First off, this is what we're talking about. That's a Greek letter. It's chi. When you write it in English with the Latin alphabet, you write it as chi, but that's not chi, it's not chi, it's chi, right? So it's called chi-squared. This is the only test we use where the outcome variable, the thing that you're trying to predict, is nominal. So what you're trying to do with chi-squared is you're trying to predict frequencies in a nominal variable. This is the only test we cover in this book where we do that. Because the z-test uses means, the t-test uses means, analysis of variance uses means, correlation regression uses means. This is the only one that uses not means. It accesses frequencies. So, for instance, you might want to know what percentage of people in a sport are right-handed, left-handed, or ambidextrous. So that's 3 categories, and what we're going to put in there is the number of people who go into each of those categories. So it's not means, it's not standard deviations, it's counts, it's frequencies. So, you know, let's say you got a baseball team, and I can't remember how many people are on a baseball team, but let's say it's like 40, all right? In a baseball team of 40, you might have 15 left-handed people. And you might have another, 17 right-handed. And you might have 8. My number's adding up? Yeah. Who are ambidextrous. And that actually is not unusual for baseball. You guys may be aware baseball favors left-handed people. And so half the pitching, half of the lineup on a baseball team is pitchers, and half of them are going to be left-handed. And then for batters, it's a really big advantage, even if you throw right, if you can bat left or if you can bat from either side of the plate, a switch hitter, it's ambidextrous. That's a big advantage. And so you'll get a lot of ambidextrous people, and you'll get a lot of left-handed people compared to the general population. In general, 90% of people are left-handed. And about 90% are right-handed, about 10% are left-handed, and hardly anybody's ambidextrous in the general population. But in baseball, you get a lot of both left-hand and ambidextrous, or people who switch hands. And so this is a situation where we're simply counting how many people are in each category. This is when you would use chi-squared. So it's not an average, it's a frequency. And this, by the way, is the chi-squared test for goodness of fit. Because what you have is a single factor that you're categorizing people on. And in this situation, the category is handedness. So that's our one factor, our one variable. And we've got 3 possible answers to that one. Now, if you wanted to, so the chi-square test for goodness of fit, that's where you use this. You can also have what's called the chi-squared test for independence, and that's where you have 2 categorical variables that you're breaking things down by. So right here, this might be baseball, okay? But this right here would be, let's just say, Basketball. Do any of you play baseball or basketball? Okay. Basketball? Yeah. Most of the people who play basketball are right-handed because there's not a strong advantage to handedness. You can make a small argument that if you are blocking shots, it would be, and you're blocking a right-handed shooter, it would be helpful to be left-handed because then you're blocking with because you're facing them and you would be blocking with the same arm. You can make that argument, but it's not really strong the way it is in baseball. And so if you had a basketball team with 40 people in it, you might expect it to be like this, like 32 and 7 and 1. And what you would do with the chi-square test for independence is you would want to see if the distribution of handedness is independent of the sport that people are playing. So we have two variables that we're using to categorize people: sport and handedness. And each person falls into just one of these boxes, one of these cells. And you can tell just by looking that the sport makes a difference, right? So if a person plays baseball, then we expect a lot more left-handed and ambidextrous people. If they play basketball, we expect a lot more right-handed people. Similarly, the interesting thing about the chi-square test for independence is that it's symmetrical. And that while the distribution of handedness varies according to sport, the distribution of sport varies according to handedness. And what that means is, like, if we know that a person is ambidextrous, we can predict that they probably play baseball. Or if they're left-handed, we can predict kind of the same thing, and we'll be more accurate more often than not. Yeah. It's because this is not a mean. It's not an average. It's a correlation, but it's not based on means. It's based on frequencies, and so it's calculated very differently. One of the interesting things about it is when we use means, you have to have sort of like a hypothesized population mean to deal with. You don't need that here. The chi-square test for goodness of fit, when you have just one of these, if I'm dealing just with the baseball people, I can say, well, 90% of the population is here, and 9% is here, and 1% is here. And those can be my proportions. And if I've got 40 people, then I can go through and say, well, I'd expect, this, I expect 0.4 here, and 3.6 here, and 36 right here. And so these are called expected frequencies. And that's what you're comparing your data to. You're not comparing them to means. You're comparing them to expected frequencies. You can get it either by using these proportions that you have from somewhere else, or you can just say we expect them to be split totally evenly. Okay? On the other hand, what's interesting about this one is when you have the two factors, there's no reference at all to anything outside. You compute your expected frequencies entirely by just looking at the rows and the column totals. And so what's funny is this is a totally, you might say, a solipsistic test. It makes no reference to anything outside of this table. And it just looks to see if the distribution going across is the same for the top and the bottom, or if the distribution going up and down is the same across all three. The most important thing to know about the chi-squared test for the final, ready? It's the most important things. Number one, that it's an inferential test. That actually is a question. You have to know that one. It's an inferential test because you're using sample data to make a conclusion about a population. The second thing is that it's based on frequencies or nominal variables. The chi-square test is based on frequencies or counts of a nominal variable. The third one is that there's two versions of it: the goodness of fit for when you have a single factor, and the test for independence for when you have two factors. Also, this thing where I said you don't need to use the mu, what that means is that this is an example of what's called a non-parametric test. And what that means is it doesn't refer to any parameters. A parameter is something like the mean or the standard deviation of a population. This doesn't refer to those. So it's non-parametric. And what that's nice is that means that you can conduct this kind of test when you have no information about the general population. You can do it anyhow. So that makes it a very flexible test. It applies in a lot of situations. Yeah. That's correct. No, it doesn't have to be the same. You don't have to have the same totals going across. I just happened to do it in this case. You could do it with 80, and it would be looking, is it 2 to 1 all the way through, or does it vary? So it doesn't have to be equal. We have 2 minutes left. The recording stops automatically at 8 o'clock straight up.
Repeat something. You said that was for public question.
Let's see if I can remember them. It's an inferential test. Okay, chi-squared is an inferential test. Second, it's the only one that uses nominal variable as the outcome. Third, there's 2 kinds. There's the goodness of fit and the test for independence. And fourth, it's a non-parametric test. All that stuff's in the book. Folks, we are done. Please take the final sometime in the next 7 days, okay?